Hi there. Every year I come here, there seems to be like an extra 50% of you guys. Holy crap. I believe Jasper said something about aiming for 500 people next year. All right. Jesus. A couple of years ago, I had an opportunity to sit down with David Turner, the author of Miranda, which was the sort of predecessor, or the moral predecessor to Haskell, at the IFIP working group 2.7, the little working group that like originally wrote Haskell. They invited me to like watch and talk to people and stuff, and it got me thinking about the way that we used to compile lazy programming languages before the world shifted to the approach that we use in Haskell. And so what I want to talk about today is sort of an alternate history. What if we were to go back to the way things were done in like 1982 and fork off and explore a different direction? What did we lose to get what we got? And I'm not going to necessarily provide all positive answers and, hey, we should do this for everything. But I think there's at least some insight that we can gain from kind of exploring the way that the evaluation of lazy programming languages got to where it is today. Okay? And so, to that end, I cut this down rather drastically for time, so I dive straight in by building a lambda calculus. So here's just a Toy Lambda Calculus. We have variables, we have applications, and we have lambdas. And every time I bring a lambda, I bring another variable into scope. So if I have 3 variables of type A, I want 1 extra variable, so nothing is my new variable. And now I don't have to deal with names. This is like a de Bruijn indexed, locally nameless sort of representation for the lambda calculus. The monad does binding with capture avoiding substitution. And I spend a lot of time here dealing with names. It's one of the things we do. We throw little lambdas around. But one of the things that we do in Haskell is we decide we don't like lambdas all over our code, so you'll find a lot of people rewrite things into point-free style. Okay? And there's an algorithm associated with compiling like putting things into point-free style. You can always do it. You maybe shouldn't do it because it looks ridiculous sometimes, but it's always possible. And that algorithm is actually very deeply tied to the roots of Haskell. It's the same, like if you ever run PL on LambdaBot on IRC, or go to point-free IO and like just plug in your expression and it spits out something horrible involving apps and lots of dots and flips and consts and stuff. That algorithm is a pretty storied past that goes all the way back through some guy named Haskell to another guy named Moses Schoenfinkel, who actually came up with the thing. But in the proud tradition of all things mathematics, everything is named after the wrong person. So what is a combinator? A combinator is just a function that has no free variables. Okay? So when we talk about parser combinators, they're top-level functions. And in general, so we can look at a timeline here. I expect there should be roughly 1 paper reference a minute. I apologize. I will put the slides online afterwards. So the sort of origin of this is something that more people in this audience will be able to read than I can. This paper by Moses Schoenfinkel way back in 1924. He was a Russian mathematician who happened to show up at Göttingen in the 1920s, and then he wrote this paper, and then went back to Moscow, went crazy, died in a sanitarium, and then his neighbors burned all of his papers for fuel. So we don't really know what else he did, but he did this. So he came up with the sort of like the notion of combinators, the original combinatory basis that Curry became famous for, and then kind of went away. Then Haskell Curry wrote a paper also at Göttingen in 1930, which is the one that everyone cites. And then fast forward until 1979, and there's an improvement that David Turner made in how to compile from the lambda calculus down into combinators. And then there's like some other references that just going forward. If you want to learn more about combinators, there's this book by Smolyan on Tamaka Mockingbird, and then this other paper by Sabine Broda, and her paper is also a pretty good introduction to all of the attempts to make this stuff fast. But let's just build a little toy combinatory logic. So this is also going to be a monad, kind of uselessly in the same sense as the lambda calculus one I had before. So the monad for the lambda calculus I built before was using substitution to do, well, substitution. And here we can just bind into terms that involve variables, applications, and this small set of functions that you can translate any term in the lambda calculus into. And so what are they? We never use them with these names. So S is app for the reader monad. It's like an application, but we're going to plumb a Z down into both sides. We're going to take some piece of an environment and pass it through to both sides of the application. K is const. I is the identity function. B and C are special cases of like playing with S and K. You can build those out of the simpler parts. So that's dot and flip. And then Y here is recognizable to us as fix. And if we were to build the algorithm that's used by PL, it's this notion of abstraction elimination. And this is kind of going back to the Schoenfinkel encoding because I can fit it onto a slide. We take variables to variables, we take applications to applications, and whenever we go into lambdas, we have to compile the lambda. And if we have lambda xx, that's the identity function. We have lambda xy, where it's something else, then it's just a constant of a given variable. And we carry on and do checking to see whether or not the variable occurs in one side or the other. Tells us whether we should use S or B or C. Because you can look at B and C as special cases of S, where what we've done is we've either passed the Z into one side or the other side or both. So B or C is telling us which way we should send that extra piece of information. So the job of S, B, and C is to plumb an extra piece of environment around that Z. And that's intuitively how we're dealing with variables. That make sense so far? Okay. So this algorithm is pretty much what LambdaBot uses for PL. So the way history actually went is in 1982, John Hughes wrote a paper on what he called super combinators. And it was floating around and kind of in the zeitgeist right at the time, which is the idea of building a combinator set that is like particular to your program. And super combinators are not quite technically combinators, they can reference other super combinators. But the idea is that it's actually much more efficient to build an append combinator than it is to build append out of SKI, et cetera, because you spend all this time mangling the SKs and Is and less time actually doing the work you really want to do. And so at the time, this was maybe a very rough, like 40% kind of speed improvement. And then later on, Leonard came along with this, like his compiler for LazyML, and talked about how to implement super combinators efficiently. And so what he did was he said, well, you can write a little imperative program that implements each one of the super combinators. You know what it has to do, just do it. In his case, it was spitting out a little bit of bytecode. And then later on, Simon Peyton-Jones, we have the spineless tagless G machine, which is the model that we can recognize in GHC today, which is execute super combinators, and here's a bit of gluing around it that still feels like we're working with a functional language. We have lets that create things, cases that analyze them, and then inside of everything is just these super combinators that we're evaluating in sort of Leonard style. I hope this didn't, I don't think I lied in any of that in any meaningful way. And then later on, there was some improvements by Simon Marlowe and folks where they said, well, a lot of the time we don't want to just jump blindly into unknown code in order to do case analysis. So if we use the least significant few bits of our pointers, we can throw some tags in our tagless machine and use it to identify which cases we're going to evaluate. And that gets rid of like about 70% of the overhead of just blindly jumping. But in order to evaluate Leonard's model or Simon's implementation of Leonard's model, we ultimately do a jump to an unknown address. How many people have been paying attention to security news since the beginning of this year? Okay. So at the beginning of this year, there were 2 exploits that were released sort of haphazardly. One was called Meltdown, and one is called Spectre. And every GHC thunk, every time you jump into unknown code like this, you are exhibiting a Spectre v2 vulnerability. That means that what we can do is I could poison your branch prediction table by saying, hey, look, predict that you're going to jump to some other code. The CPU will speculatively execute that code, and it'll realize, oh, no, that was wrong, and undo what it did. But it'll leave side effects in the caches on the CPU that you can then use timing attacks to read. Okay? So I have a bit of a concern here. There were some attempts at mitigation that came out of the LLVM community early on. There was a technique called retpo lining. I don't know how many people have heard of retpo lining. Okay, so it's actually a reasonable cross-section. So the idea of retpo lining is instead of jumping to an unknown address, what we'll do is we'll push the address that we're going to, and then we'll return to it. And that almost works. Turns out that apparently Skylake Plus still screws up if that cache gets too full. It then falls back on the other branch cache. So I really don't know how to fix this. So so be careful if you're running GHC on computers that also run other people's stuff. And you have security conscious application needs. So last year, I talked about C++ for a couple of hours. And I promised Jasper not to do so again this year. So there'll be a little bit of assembly references here, but no C++ this time. So thankfully, Gabriel got our requisite amount of C and C out of the way, so we can pretend we're not just a Haskell conference hackathon thing. So here's an observation. So the technique I talked about last year was to try and write programs that use all of your SIMD lanes to execute the same program on different data. So the usual technique that people use to make use of the SIMD instructions on their CPU is to try and take a loop and then unroll it enough to spot that they're doing a bunch of common additions on neighboring elements, and then hope that they can commute things past each other, and then optimization happens, and then if you run with -03 or something like that, then maybe your compiler will optimize this thing, and you just hope and pray. An alternative is to use this technique that was used by the Intel SPMD program compiler. And it sounds super official, but it's basically the effort of this one guy, Matt Farr, who was working at Intel at the time, which is to do kind of what the GPU guys do, which is to run the same program but with multiple copies of the data. So when I give you an int on a program on a GPU, it's actually like a SIMD register full of ints, and those are really wide. Like it's 32 on NVIDIA, it's 64 wide. 64 integers wide. So these are 2048-bit registers on AMD's graphics core next architecture. And then whenever I read from memory, it's gathering from different addresses in memory. And whenever I write to memory, it's scattering. So, and if I do like an if, what I do is I keep track of like a current execution mask. Which lanes do I care about? And if I go into an if, I'm like comparing x is less than or equal y. I'm computing a SIMD Boolean that tells me a mask of the places that wanted to go down the true branch of the if, and I AND it with my current execution mask, and I narrow the focus, and I keep going down. So I keep losing coherence as I branch away. But the general computational model, as long as I can kind of keep things with all of my lanes firing all the time, is generally that I'm getting about 8 times the throughput minus a little bit of extra instruction overhead. So these usually wind up being about 6x in terms of general performance. So I'm willing to do an awful lot for a 6x performance improvement. And so when we were talking about the performance of the sort of current approach, we said, well, with Lehnert's technique, evaluating super combinators was about a 2x speed up. And then we were able to get about 3/4 of those to go away by using dynamic pointer tagging and whatnot. So we got about a 6x speed up on the table there. So can I even get into the same ballpark just by going back to the old technique and evaluating it using like a very modern compiler evaluation technique to run SIMD code? So I would run 8 threads at a time using the individual lanes of my SIMD unit on one core. So that's the trick. One of the tricks that I'm playing with here. And there's some interesting notes here. One, it bypasses the Spectre issues. This is never doing blind jumps. And it's not bad. So there's a couple of issues along the way, which is that this is unfortunately not the entire story. So compiling down from the lambda calculus into combinators involves an expansion in the amount of code that you have. So Curry and Schoenfinkel's original algorithm could blow up the terms by a factor of O(n cubed. And the reason why I mentioned Turner's name earlier when I was talking about the algorithms for compiling down to combinators, Turner came up with an improvement to those that gets it down to O(n squared. And if we look at just S, K, and I, we can kind of, like I said earlier, we can talk about S as if it was an application that's passing an extra environment, Z down. And K is, yeah, ignore that environment, and I is use it. So you can view this as one way to read the combinators as just manipulating an environment. And they're working one variable at a time. So it's intuitive that you'd kind of need like O(n squared, because I could build up a lambda that takes n arguments, and then I have to work, if I have to plumb it around one variable at a time, it sounds n squared. But we don't really have to work one variable at a time. I believe Francesco's hiding in the audience here somewhere. Francesco Mazzoli? Where are you hiding, Francesco? Oh, did he wake up? No. Anyways, he's here somewhere. So he earwormed me last year at Compose about his little, he wrote a little blog post on a well-type suspension calculus, where the idea is, like, let's go back to the lambda calculus, and instead of working with de Bruijn indices directly, there's an idea of like building a substitution and passing them around as explicitly part of my terms, and then pushing them slowly down through my syntax tree to get them out of the way. So I work with the syntax tree as if there weren't explicit substitutions in it, but this lets me be more efficient than a de Bruijn index, because working with de Bruijn indices, I have to walk through the whole term and then bump a bunch of counters. Okay, my bound library uses one technique to kind of dodge that some of the time. This is a much more general technique. But there's been a bunch of work that goes back to Abadi and Cardelli and Lascon on these notions of explicit substitution calculi. But when Francesco came up to me with it last year. I had no knowledge of the prior art, and I sat down and I said, well, maybe we can just build a different thing. And it turns out you could build one of these out of some notion of catenable random access list. So grab a finger tree, grab a SKU-MITRE random access. Actually, you need to use it probably like a finger tree. And you can build a version of this where it takes log time to glue two partial environments together. Like, give me some of the environments that I want to use. Give me another some of the partial environment, and I can merge them together. And then if I were to drop off a prefix where everything's only referencing things further on in the environment, it keeps well-formed environments still well-formed. So there's a version of this that should exist, damn it, that is log time to glue the environments together, and then pushing things down slows things down by a factor of a log. But when I'm indexing into this, now indexing is log time as well. Because what we're doing is, if you think about it, if I built my environment as a tree, I could do log time indexing. And then using the SKs and Is and stuff to navigate through isn't working one at a time. We use logarithmically many of them to find the right one inside of the structure. Okay. So that hints that there should be something n log n available. I do not have an implementation of it that fully works. And the thing is in practice, it's probably not worth doing, but I think it's an interesting theoretical curiosity that one could do better than the n squared that we had from Turner. So that's one of this is going to be a collection of mishmashed results. Some of them work, some of them don't. And then the next one that kind of came up when I was playing around with this goes back also to the early Leonard, Hughes, et cetera era. There was as part of John Hughes' PhD thesis, he identified a problem, which is that lazy programming languages leak memory if you don't have help. In particular, if you don't have some form of parallel reduction, then like doing break on new lines or something like that will leak some memory that it shouldn't have to leak. So it was a problem that was identified by John Hughes. And then Phil Wadler wrote a paper on fixing some space leaks with the garbage collector in 1987. And then later on, one of Leonard's PhD students, Christina von Dorian, she did a paper, or a PhD thesis on generalizing this to what she called stingy evaluation. So the idea was, with what Wadler did was said, if I have first applied to a pair, the garbage collector should turn that into the first half of the pair. Rather than hold on to the first function applied to a pair so that it will leak the other half, the garbage collector should just do this work. So the idea here is, in general, if you have any kind of computation that will shrink the heap, you can view the size of the heap that you have to move in the garbage collector as an amount of fuel that you could spend doing reductions, as long as those reductions are contractive on the heap. Yes? How do you know it's safe? A is already there. If I have first applied to an already evaluated pair, the thing's already on the heap. So all I'm doing is dereferencing. This is not going to evaluate the pair. This requires the pair to already be present. And so this is, in Wadler's case, this is generalized to any field selector applied to a data type in Haskell. If you look inside of the runtime system guts, there's all this stuff to make the garbage collector do all this forwarding. It's actually quite complicated. And I believe Ben Kamari sat down and did some work on removing it to test like how bad it is without it. And you can't even get like a stage 2 compile of GHC to build if you disable this optimization. Yeah. So that's somewhat important. Whenever I'm told someone's going to evaluate a lazy language on top of somebody else's garbage collector, I always kind of look at them funny. So one of the things that I'm really been impressed with, like with GHC.js, is that Lauta is a crazy man and went through and did all of the stuff to do the heap traversal to find all of these things, partially to implement GHC's finalizer semantics, but also to avoid this class of space leaks. So So if we go back to stingy evaluation, this more general notion, you could teach your garbage collector to do some reductions. Do I have an actual int wrapped around a number, like int constructor, and I've got a primitive addition here? I can do the additions because it will result in a smaller heap, potentially. And so there's several of these combinator rules that are also stingy. We can evaluate k, we can evaluate I. ASK is this k underscore thing, which we could set aside. Each of these is going to shrink the heap if you were to apply these rules. And so there was a paper by Hudak and Krenz, this combinator compiler for functional languages. That this was pretty much the last gasp of combinators. There's one more paper that I'll mention. It's about the same year, maybe the next year. And it was, they were compiling a lazy language down into combinators, and then they were applying a whole pile of rewrite rules to simplify things. And they weren't baking them in as into their actual like graph reduction machine. They were simply adding these rules to make smaller program object files. And so some of these rules could be applied by my garbage collector on the same kind of basis as the locally shrinking in their object files. A couple of their rules are not technically guaranteed to always shrink the heap, so I didn't include everything. So what do I want out of this? What I really want is to get Wadler's rules as an emergent optimization. I want to say, if I were to church encode my pairs, or Bohm-Berducci encode, or Mogensen-Scott encode, whatever I want to do, like pick an encoding that gives me a lambda calculus encoding of pairs or whatever data structure. Can I get the field accessor reductions to be stingy evaluation rules, applications of stingy evaluation that just work? And to get there, I need a few more rules than this. It's somewhat unfortunate. So these are not enough to pull it off. So evaluating K's and I's are it's obviously stingy. K, there's X, it's right there. It's just like the first of pairs. We're taking one of the, if I have K applied to two arguments, I can always turn it into the first argument. You know, I applied to an argument, why is the I there? I could have the garbage collector just remove them systematically from the system as I go. But I can't evaluate S this way because S is going to copy Z. So also in '84 apparently, was this paper by Bill Stoy and a couple of other folks on some practical methods for rapid combinator reduction. And they were working on a thing called SCIM2, which was a SKI machine in hardware. So they were talking about the microcode of this architecture. And I thought I was being super clever when I thought, oh, I can apply 1-bit reference counting to my combinator machine, where what I'll do is I'll just keep track of whether or not I've told anybody else about an application. And if I haven't told anybody else about it, it's mine. I can secretly mutate it behind the scenes, right? Look, uniqueness. The clean folks who might be in the audience should be proud. But unfortunately, I did not, I found it in like an old garbage collection book that I'd read way back in the day. I thought this was a really clever application of this technique. And then I found this paper by Bill Stoy, which was actually the paper that invented 1-bit reference counting. So I felt like I was on the right track, but I was somewhat disappointed that it wasn't terribly novel. So it turns out that working with combinators produces a lot of garbage, which is what caused people to have to care about this stuff. So if I hold a unique reference to the root of this, and there's a unique reference to the left, and a unique reference to the left, and and we get all the way down to our S, then I can afford to repurpose these applications to build these applications on the right. This doesn't actually expand my heap at all. If any one of those references down or these two references down the chain are not unique, then I can't do that. I can't mutate it in place to make this thing happen. But if so, I can avoid going out, grabbing 3 memory cells or whatever from my my heap, and then rewriting and then pointing. I can just do the mutation in place. And similarly, so what I did here was I said, well, when we duplicate z, I'll just basically be setting a bit in the z, in the pointer, the element for z. And that'll just tell us whether or not it's unique. So we can use that to know whether or not we can do some of our s's and stuff in context. And we can do c's, which doesn't actually have to duplicate anything because e only gets sent down one direction. B only sends it down one direction. K is clearly contractive, etc. And so we can build up a pile of extra evaluation rules that require uniqueness to be stingy. And if we go apply that algorithm for abstraction elimination that I wrote at the beginning, we can say what is first and second and pair. And these are all built out of things. C's and I's and K's and B's and C's and C's and I's. All of these are the things that are well behaved. They are all at least locally going to produce smaller results. So it's not, I'm not quite there. I don't quite have this thing doing Wadler's rules, but I get 99% of the way there. There's like one place where I need an extra piece of uniqueness to avoid having to expand my rules in order to show that this is contractive. So this is one of those cases that just didn't quite make the cut. So sorry for building that up and then failing. But I spent a lot of time on it, so I figured I should share. Negative results are still results. The next observation here is this. If we look at those rules for combinators, almost all of them have an interesting property. If we look at like, where's our S rule here? Here we go. If X, Y, and Z, if none of those are underneath another one of them inside of the heap, after I apply this graph reduction, that's still true. So if I have a directed acyclic graph, and I apply any of the graph rewriting rules that are available, that are given for how does a combinator evaluate, the result is still a directed acyclic graph. The only difference is there's one rule, Y, which is implemented usually like fix in Haskell, where we say, fix of f is, well, let's let x equal f of x. And we kind of make an app cell that points to itself as its tail. But if you're willing to let that thing blow up in space, then you can also still have this property. This opens up some interesting options. One in particular that's near and dear to my heart is the idea of hash consing. So I can actually hash const an entire heap for a little lazy language. And the techniques for doing the hash consing here, I would basically borrow out of the community for doing binary decision diagrams, BDD. ROBDDs are hash const in much the same way. They have almost exactly the same structure. Everything that's used to make CUD fast can be applied here. And there was a paper about 10 years ago from Ilko Dostra on maximal laziness, talking about how to basically do this hash consing, or they used it for nicks, if I remember right, and saw like a 40% speed improvement there. So there's an interesting observation there. But if I apply this notion of hash consing to the heap, I get something, it's almost like the freshman dream of Haskell, which is when people first encounter Haskell, they often assume that everything kind of memoizes automatically, right? Like if I call a function with the same arguments, it'll just magically remember that and just do the right thing, right? Right? The overly simplistic understanding of what laziness is. Well, what if I were to use my heap as a little hash table? Like I'm going to hash const my heap and build it up, and then so it's a little like cuckoo hash or whatever. And then use a really boring, lazy reference counting scheme. Because we're acyclic, I can reference count. So a lazy reference counting scheme is going to say that when I decrement my count to 0, I do not immediately go into my children and decrement all of their counts. What I do is I put the value onto the free list, and when I pull it out of the free list, then I decrement the counts of my children. So it gives you truly constant reference, like unamortized dereference time. So why do I care about that? If I were to do so as like the zombie memory cell is still available until it gets recycled on the heap. So that lets me, because I can find it through the hash consing table. So what would happen is if you wrote naive fib, for instance, and it did the recursion down one branch and said, oh, what's fib of 10, fib of 11, etc. By the time you come back up the other direction, it'll memoize the result, assuming that you have enough extra space on your heap. So the empty space on your heap immediately becomes a sort of memo table for every function application, which is kind of adorable. I don't know that it pays off enough to justify the fact that you're basically getting about 50% density on your heap. I honestly don't believe it does. If you have particularly expensive evaluations, then it might be worth doing. That's one of the things, like Nix is going off and saying, hey, do compilation for me, please. You know, those reductions are super expensive. You don't want to do them very often. So why do I care about all of this? I've been playing around with a little toy language that is becoming dependently typed kind of by accident. And if I look at the way people implement dependently typed languages, there's usually like 3 competing concerns that you have. When I go to build the compiler, I have to have some kind of intermediate representation that I can do evaluation on efficiently. I don't need IO refs and stuff in it. I need efficient evaluation. I also need efficient unification, because I'm going to do higher order pattern unification all over the place inside my type checker. And I also would like to get sharing on those terms, because these terms and types, et cetera, wind up being pretty darn big. So I would like to have a representation that's automatically hash const all the way down. And so there was a Stack Overflow question. One of the reasons I started thinking about this was there was a Stack Overflow question that was answered by, I believe, Connor McBride sat down and answered, like, what would it look like to build like a dependently typed lambda calculus, but in like the combinator style, where he's like pi is a combinator, et cetera. And he gave an answer, and it was horrible looking, but it stuck in my brain. And there's also this paper by Daniel Doherty, which is the last paper I can actually find, really, that talks about combinators at all in any sort of serious capacity, on doing higher order unification, higher order pattern unification using combinators. And so it turns out you have to do a couple of extra tricks. But there is a way to talk about higher order pattern unification directly in combinators. So if I'm looking at how do I evaluate my little dependently typed language at compile time efficiently, if I can spit out these combinators and I can get into the same ballpark as the speed of doing an evaluation directly in Haskell, it's like having normalization by evaluation directly on my terms, but I don't have to copy out into some kind of value form, do a bunch of work, and then copy back, doubling my memory usage, and then hope I can hash const everything away afterwards. So it seems to give me one representation that I could use everywhere through that compiler. I don't want it's not a runtime representation. I wouldn't want to ship this as the way that I run my code in production. You know, I can't build IO refs here. The whole heap has to be acyclic. But when you're type checking, you don't have IO refs in your type world. So this has been the little thought experiment that I've been kicking around I was kicking around like at the beginning of this year for a couple of months. I did a lot of work on it. I lost 3 laptops in rapid succession to an Apple power supply deciding that it was going to kill laptops. I didn't know that was even possible. I have like 9 Apple power supplies spread around my house, so I figured losing 3 laptops to identify which one it is asymptotically optimal. So unfortunately, a lot of the code that I had that was working on this went away in that incident. But that's pretty much what I have. As we've seen, we've got a pile of implementation techniques that all kind of work on this small combinatory basis. And there's some interesting things here where if I look at that small combinator basis, it's the kind of thing that I could feed to a GPU and write a little compute kernel that can compute with. And very recently, it's become possible to get a single kind of compute shader that runs across all platforms that I really care about. Molten VK was open sourced thanks to Valve's efforts fairly recently, so now I can run Vulkan compute shaders on pretty much every platform. So now I have this interesting dilemma where if I start putting this together, it's like, please upgrade your video driver to type check this file. And a good excuse for me to ask for a better video card when I need to work on bigger programs. So, thank you very much. I don't know if we have time for questions or what have you. Any questions? Somebody can run around with the mic if anybody has any. No, I just see a sea of blank stares. All right, Gabriel. Oh, all right.
So you mentioned earlier that if you try to build a functional language on top of a stock garbage collector, that you're going to run into problems that I think you said Wadler had worked on solving.
Yes.
That describes almost Nix to a T, right? So does that mean there's low-hanging fruit for improving Nix's garbage collection?
Probably. I actually don't know how Nix's garbage collection is implemented.
It uses the Bohm garbage collector.
Oh, okay. Well, the Bohm collector is that, like, Hans Bohm basically just realized that in general, if you just mark and sweep, it generally doesn't blow up. And he tries to make he makes a pretty compelling case that seems to actually, like, the fragmentation isn't a real issue for them and stuff. Oh, I see Manuel.
Interesting idea, indeed. So you wanted to recover the performance improvements of super combinators and stuff like that by using 8-way parallelism or something like that in your SIMD instructions.
Yes.
That still leaves you with figuring out which things to actually run in parallel. Now you're in a purely functional setting, so you have no references or anything. But I mean, as we know, it depends when you do reduction of lambda terms. It can be depend a lot on the program how much parallelism is actually available in terms of reductions, and finding the redixes which you can reduce simultaneously can be tricky. Do you have a story for that?
Yeah. So what redexes to reduce is if I'm oversimplifying. So one of the things I didn't mention here is that you really need to start adding, like, seek and par as combinators to your vocabulary here. So you have some way to actually say, do more than one thing, please. And so once you have, like, seek, at least, you know you have to do both reductions. With par, generally it's like, please do this one if you got some time. So here, if I'm going to be doing 8 at a time or 64 at a time on a GCN chipset, or if somebody wants to come up to me and talk to me about the bit slicing thing, I have a thing that gets me 2048 at a time on AMD. So that's a lot of threads to be reducing at once, and I do need a good supply of sites that I have to reduce. I have a few things here that help. One is the stingy evaluation side says, here are reductions I can always do. Like, those I can apply, like, I can just kind of en masse run over the heap and say, does this apply? Do it. So that helps a bit, at least at garbage collection time. That's not a supply of, like, real reductions that are running all the time. But it's really, for me, the moment the only, like, the only thing that's supplying the food chain here is type checking a thing, I need the result. So I'm doing comparisons on terms or something like that. Like, do these things unify? Keep forcing my way down. And, like, these par and seek connectives and whatnot.
So, follow up, if I may. Kind of this leads to the question, because usually when in a dependently typed language, you do everything inductively. And as we know, I mean, from work on parallelization of functional programs, it's the inductive structures which are usually hard to parallelize. So when we do things like functional array CLPU languages or so, we prefer array structures or similar non-inductive structures.
It's so, like you worked on something called data parallel.
maybe.
Yeah.
But then the question is, I mean, the motivation for doing everything inductively in dependently typed language is basically historical. So can we come up with a dependently typed calculus which is not just based on inductive structures, but also has structures which are inherently more suitable for parallel evaluation, because then your problem would be a lot simpler.
So I have a so this is the story I've been kind of investigating at the type level. I have another story that I've been investigating for how to do evaluation of programs that are designed to run sort of SPMD style. How would I build like a SPMD based ML? Right, an ML that's like more or less like the Intel SPMD compiler, but for like an ML, like upgraded just enough to have like garbage collection and varying like algebraic data types and stuff like that. And so I've been kind of investigating that space, like how do I get just enough width to make full use of the cache lines. I'm not quite ready to give a talk on that one yet, though. I sort of did an impromptu hallway track version of it yesterday, but. That is unfortunately not recorded for posterity's sake.
Yeah. You need vectorization for your types.
Yes.
Thank you very much.
Thank you.